Okay, I'll wait 2 more minutes. I'll just say, so there seems to be a issue with Archer 2 today. We are expecting it to, it's being looked at right now. The prognosis is rather positive. So what we're going to do is talk through some of the code examples from the lectures yesterday and show you some solutions. And then we are going to start on the next lecture. We are hoping that by around 11 o'clock, we may have the system in a better shape and we can continue to do exercises for the rest of the afternoon. If we're not in that shape by lunchtime, we will look to have alternative options. I think we probably have capacity with the rearranged date to manage this anyway, but we will have to play it by ear a little bit. So for now, I'm going to start discussing exercise 2.02. So this was kernels yesterday. So let me just get myself sorted out a little bit here. Sharing and the like. Yeah, it's I don't know what the prognosis is, the reason for it, but pretty much the entire Archer 2 has gone down. So this is not just a GPU node issue, but it's sometimes this happens. It's part of running a big service, and like people do interesting science in it. Anything can happen. Yeah, just another day in the office, like Juan says. So let me just get my screen up a little bit larger. There we go. Okay. Just waiting for that to come through and you actually see on the screen. Okay, great. So just zoom a little bit. So yesterday, one of the key sections and the key things to learn about GPU programming is the ability to launch kernels. So I went through with you through this material yesterday afternoon. And at the end of this, and what we're really saying is that you can replace simple loops with kernels that you can launch. And the key thing here is that you express the operations you want to do on the device in a kernel. We've pre-named this with the keyword here in this piece of code. And then you decide on the set of operations you want to do. And the runtime, also called the API, provides you some handles on how you're going to partition threads over the work you want to do. So, for example, what we're doing between these two cases is we're taking some for loop over an array length, and then we are updating the value of results by just putting 2 times I in it. Okay, and that's what you'd normally do on a CPU. So do this for loop, run over a number of iterations, and complete. The compiler might try and do something smart about trying to split this up over cores if it can do something like that, but it's likely not going to. You have to provide some OpenMP directives or something to do that. It's not really going to be able to parallelize that on its own. What you're doing on the GPU is slightly different. You're saying, I'm going to have a kernel, and I'm going to have to return some pointer to results. I have some pointers to results I'm going to take. I am then going to update that value. That's the body of the loop. And now, instead of just having a for in here, I've got a number of threads. And each thread is going to do the same piece of work, this piece here. So I is equal to thread index. So this is thread 0 is going to do part of the results. So this is like when we saw yesterday. I'm going to show you a very... Sorry, just to save me having to... I've shared a specific window and not my whole screen, haven't I? Sorry, I'm just trying to bring up my slides from yesterday morning to try and elucidate some of the things I am saying. Of course, that's done that. So I have no idea why we have gone onto that. Sorry, let me just get myself straightened out a little bit. Too many screens and too many different tabs to be doing things on. Okay. I want this to be F11. I showed a window, not a whole screen. That's what I wanted to do. Okay. Right, I'm just waiting for that to come back through. I'm just trying to get to the slide on relevance. This. Okay. So we have a one-dimensional problem in our example from here. We've got a set of results, and we're iterating over that. With every single element, each thread is doing independent work. That is exactly with what we were doing from here. Sorry, I'm trying to show slides from the current slide. Right, that's this. Okay, each individual thread, each individual worker does an operation, and what we do is we extract the loop construct out, and we're going to provide threads to cover all the elements that would have been within the loop. What we can also do is then by hand block this up. So we're saying there's independent blocks that can be executed on a compute unit, and we can by hand explain to the compiler what blocks, to the runtime, what blocks can happen independently and what operations within a particular kernel can be executed. Right. So that's what we come on to down here. And when we launch an one-dimensional example, we have one block in each direction. We can have each of the 3 dimensions, and we launch the total array length in the first direction. Okay. The kernel launch is specified by calling it my-kernel. So the name of the kernel is my-kernel. It's just the name of the function name here. And then we have to use these angle bracket construct to put in the blocks and the threads per block. We can then make this more complicated using the blocks if we have more than one dimension in more than one block. We then have to change our kernel to accept information about the block dimension and the block index. So effectively, you're now saying, I'm going to run threads X that goes from 0 up to the dimension, the size of a particular block, and then how many blocks have we got in total to go through all the elements within the size of the array. It's going to cover all the elements that we want to update in the vector results, the array results. This requires us to be specific about how we determine things like the threads per block and the array length and so on and so forth. We have to calculate these and provide them to blocks and to the launches of the kernel inside the angle brackets. And we need to make sure that we have enough blocks to cover the full array. We don't if we don't have a certain number of elements that don't fit wholly within an array, then we're going to need to make sure that we have an additional block, and part of that block will run idle effectively, because you'll have to state to it, do not run these ranges above a certain point. Okay, so that's a one-dimensional example. We'll come on to two-dimensional example afterwards. I'm just going to show you the code in a second of what that looks like in practice. The other thing to say here is the grid determines the total number of blocks. The block dimension tells you the number of threads per block, and you're going to use these to implement a particular kernel. So the exercise itself was to start from your previous implementation where you looked at data movement and then implement the particular kernel called my kernel. So if I've got the right window open, that's not the right window yet. That's the wrong one. So let me make that a little bit bigger so you can all see. So this is section 2.02. Okay. And we've also got a submit script in here, which is just going to make everything go badly by just cat it out. That's helpful. Okay, all we're going to do is we're going to launch a simple job. We'll run the GPUs, run on a single GPU, and we're going to run our whatever program we use for this. Build it. So I'm just going to use Vim for simplicity. So what we're asked to do, we're asked to implement a simple operation, x equals ax for a vector of x, type double, and some constant a. So we're just doing our doubling example. In the previous case, when we did data copying, all our example was doing was testing. We could put data from one for the host to the device, from the CPU to the GPU, and copy it back. And the values are all the same. What we're doing here is saying, when I copy data to the CPU to the GPU, I am then going to double every single element, and I'm going to take that back to the CPU and test that's the same as I would run on the CPU code. Right. So what we are doing here is we have a number of blocks and a number of threads per block, which are defined as macros, array length. Okay, so these are all independent, but we are lucky because at the moment our array length is 256 and our threads per block is 256. There are limits to the sensible number of threads you should have per block in order to be performant. And we've got our constant A set. We also have our host X, which is our input array, and our H out, which is our output array, and DX, which is our device array. Apologies if you can hear a very annoyed cat in the background. Right. What we are trying to do is add in a new kernel that we want to run. And we've also got our error checking code that we're going to want to use as well. So let me just get in classic Lupita style. I have the one I made earlier, so I can show you this smoothly and not make some obvious mistakes. So up here, we're going to write a new kernel. And now the exact instructions say define some prototype, call it global, declare and initialize the variables. 3 hold the number of blocks and the number of threads per block. Generalize it, going to treat the number of blocks and problem sizes, not whole numbers of blocks, basically. So implement something simple and then be able to change these 2 values. So to begin with, we're just going to implement a kernel. And we're going to start with global void kernel. We take an int, which we're going to take is some. Let's do the simple version first. Let's take our double a, which we're going to take as just a constant value, and we're going to take double, which is going to be our result. Now, initially, we just want a simple case for this, so we want int I is going to equal thread id x.x. Okay, so that's my thread index which I'm using, and then I'm going to have some result I, which is then 2 times I, as we expected beforehand. Okay, that's all I needed. Check, obviously wrong there. Okay, so now I've got my kernel set up and it knows about how to have a thread index it's going to run over, and because we're going to use the fact that my array, the array length is equal to the threads of a block, every single thread in the first block is going to get an element of the array, do the doubling, and then now what we need to do is call the array. So more sensible. So here we go. Let's remember the process of our program. So we have some hx, which is our input. We have some hl, which are our output. We assert that these things exist. We fill our input with just ones, multiplied by the position in the array. Hout will just take zeros, so it's not going to have any output initially. Dx exists, and we've given it some size somewhere. We've allocated it, sorry, we have allocated it here precisely with the size SZ, which is the size of our array that we need. Let's just double check that SZ is actually set to a sensible size. Yes, it's set to the array length of times the number of doubles that we want. Okay, relative to our main function. We are then copying the data from hz into the device, into hx into dx. Remember, it's destination, source, size of the copy, and the direction of copy, host to device is what we're doing. Now we want to call our kernel here, because now we have the data we want to double on the device. So let's do the kernel call. So what we have is my kernel. We're going to need some blocks, and we're going to need some threads per block. Okay, and then we're going to need our input. So here we're going to take our A as our input, which is just our constant, which we're doubling by, and our dx, which is going to be our results vector. And we do the usual thing we forget. Have we defined A somewhere? Yes, A is defined at the top as 2 as a constant. Good. Okay. Now, what I've missed here is I have not yet defined blocks and threads per block. So these have to be. Am I missing anything in the kernel? Yeah, thank you very much. Whenever I do a program like this, and I will miss something, so please jump in like that and tell me what I'm doing. Obviously, dumb things. Else, I will try to compile, things will go wrong. That's right. So we need a dim3. We need something for blocks. And this is just going to be equal to some struct, which is going to be, for now, we're going to have one block, the array and the block length the same. Change that in a minute. And 2, we'll have dim3 here as threads per block. Okay. And this is going to be threads. Threads and block, which is this macro value, which equals to the array length. It's going to be 1 and 1. Okay. So that should be everything we need at this point. So then what else happens at the end? So this executes. It's going to, once that kernel completes, we're then going to copy from device to host, and then we're going to get the results, and we're going to test them against some value. Okay. So I've got a compilation script here. So we have loaded our modules again. We've loaded our Rocker module, our AMD compiler environment, things like this that's in the instructions, and we compile. Of course, we've got no thingy because this is the other example. This is scale. Okay. and now we have a .a.out file. Now, because we're having issues with, oh, we're up, so everything's in drain state. Okay, things are progressing in Longitude to rectify things, so hopefully we'll be able to do some tests later. But for now, that's a simple example. I'm now going to slightly extend this to show you how this can get a little bit more complicated. So at the moment, we're limited to this case where the number of the length of the array and the threads per block are the same. We aren't always going to be lucky that they're identical. Threads per block is related to how we decide that the machine threads should operate together. This is related to whatever interesting work we're trying to do. We'd like to decouple these ideally. So what can we do to improve that? First of all, we need to think about what our kernel is. So let's take a little bit of an example. If I turn this into, let's do the simple case to begin with, 512. And then to do this correctly, I'm going to need 2 blocks, which means that I is not going to be sufficient. I is only going to run up to 256 at the moment, and then it's going to run over 256 again, potentially in a second block. So it's not going to run over all the elements of results. So this is where we have to be really careful when we're programming kernels like this, because we have to make sure that we deal with the cases and have the ability to run through all the elements of what we're trying to update in the GPU. So what we can use is the additional information on block ID, X, and block dim .x. So now we can run over multiple blocks. Okay, we've still got the constraint that it has to precisely be divisible by the number of blocks, but now I can run over multiple blocks. So the only thing now we need to do, because that's given us the ability to run over a larger size and we can keep going up, is to make sure that our launch parameters are correct. So I've gone a little bit too far there. So where's our kernel launch? Our kernel launch is here. So blocks and threads per block. Well, we still said there's 1 block, so that's not correct anymore. And we said threads per block is, well, that's still correct. We've still got 256 threads per block, but we need to now provide additional parameters here. So this is whatever that macro parameter I just got out of my brain, no blocks. Okay. So we're going to have 2 blocks, and there's going to be 1,000. There's going to be 256 threads per block. Tuning threads per block is an important thing you can do in order to enable performance. Just to prove to you that that should all work, I'm going to compile it and check that we get something that's sensible. Okay, so things are coming back slowly. Finally, what's the last case? Is what if we can't guarantee that the size of our array is neatly divisible by the total number of the threads per block? So what if this is 1,000? What do we do then? So the easiest way to solve this is to provide an additional parameter here. Called int n. Okay, so it's the number of elements within our particular block. We then want to protect this because we could potentially overrun now, so we need to provide some form of statement. Now, normally there's a common folklore, or not very folklore, that's a bit too extreme, but viewpoint that you should not add conditionals into kernels. That is true if it could mean that different threads being launched within a particular block as part of an individual warp could do different things. Because what will happen is half the instructions will do one branch of it, and the other half will do a different branch, and that could generate some form of contention or race condition or something like that, and you're going to end up flip-flopping between the two different types of instructions. And that can be a problem. However, in this case, because each of the instructions I'm giving is just check the size to do something or do nothing, you're in a much safer scenario to request to add a condition. So all we're doing here is saying, if you are less than this total size of results, do something, otherwise do nothing. Okay, and that's okay. Now, that now protects the kernel from running over the end of the results array. However, we do now need to wait to change how we're implementing the launch of our kernel, because that now has a more complicated logic. So how do we work out the total number of blocks we should have if we've got a non-determinant, so a non-divisible size? I can't just handfully have a little num blocks parameter for this. May change or edit during the execution. So what do I do here? I now need to make sure I calculate this correctly. So the way to go about thinking about this is to say I need one more than the array length minus 1 divisible by the threads. Okay, so that should always guarantee that I have got one more than necessary blocks that sort of cover my entire array, and each of my blocks has threads per block. Threads to execute. I now launch my kernel and I can iterate over that. Just to prove that that will at least compile, because I'd like to obviously run this. Oh no, I've made a mistake. Oh yeah, I should have 3 arguments now. Okay, I need to provide my end-len parameter, which I can just calculate as some length of this. So this could be, yeah, this is just length. Okay, so that makes sure that we don't run at the end of it, and we can execute this kernel safely. Okay, hopefully that's given covered off any questions there might have been yesterday about that first example. Are there any questions about what I've showed here right now? Okay, so if there's no questions, I will look at example 2.03. I just want to start by sharing this slide again. So let's start by looking at the example, and then we will discuss the technicalities around it. So what we've looked at so far is a one-dimensional array and updating that. What we most often want to do is work in multiple higher dimensions. Maybe we want to work on matrices, not just vectors. This provides much greater opportunity for parallelization because the element count goes up much quicker. It's also a common pattern we expect to do in scientific computing. So in a simple set of for loops, we might see nx, ny, okay, whatever, and we might loop over the elements into loop nested loops, and we might do work on each element of the matrix. In CPUs, that's the way we'd go about this, but with GPU coalescing behavior, and what we mean by coalescing behavior is that when we go to access memory, this is true with all memory systems really, is you usually go and fetch an entire chunk of memory, not just an individual element. And what it is most efficient if you go and collect a group of chunks that are coalesced in a single line and pull them all across in one go, and therefore you can stream. So effectively the way RAM works is you can imagine it as a big grid, and what happens is the top of the sort of grid has a bunch of reader heads on it. So what's most efficient to do is read whole rows at a time, because they could go to the top, they get all read in one go, and then they can be sent off. If you read in terms of columns, then what happens is you have to read a whole list of things. You have to read every single row and only use the first element or the second element, whichever the element is value to you when you access memory. So what we want to do is we want to organize our calculations to make sure that we access stuff in terms of whole rows from the RAM at each time. That's going to maximize our memory bandwidth. So when we said yesterday, and we started by talking about some of the limitations of performance of programs, we talked that memory bandwidth is one of the key limitations of most programs, and making sure we get this access pattern to the memory correct means we'll maximize data access speed, and that will drive the greatest performance in our code. What we have to do in kernels is be very careful about how we decide to do that data access, because our decisions around indexing and things like this will drive that performance basically. So in this exercise, we were looking at trying to implement this two-dimensional kernel and try to get this up to update. So we started off with the serial version, and then we started to talk about a more complicated two-dimensional implementation. I'm not going to go through and hand code this because I'd rather spend the time explaining this. So I'm going to show you a solution we're going to be looking at in a minute anyway. But what I wanted to make absolutely clear is, show the current slide, right, this. People often have a misnomer about the way you should think about reading data when you're shown a matrix. People often start in the top left because that's how we read. And in our particular case, we're talking about two-dimensional problems on a grid. We often have a predisposition to start up here. The other thing to remember is that we are in C, so we are column major ordering, which means the columns are the ones that are stored in RAM contiguously. Those are the bits that we can access quickly, so we should read in this direction. And where you would send operations in the CPU, the consecutive elements would be run by the next part of the for loop. That means that you can pipeline data into a particular instruction processor, and it can sit there and do the same calculation repeatedly and get fed data into it. On a GPU, what we aim to do is have consecutive threads doing the same operation. So they all need to, ideally, the neighboring threads have neighboring pieces of data from the memory. And when we do that, when we're programming in C, we need to make sure that the columns are the bits that we're iterating over to make sure they go in first. Okay, that means you're going to get contiguous data access. That means contiguous threads are going to have contiguous data. That's going to drive performance. That way, an individual warp gets a contiguous set of data, executes, that's the quickest thing to read to get going, that executes fastest, and then picks up the next piece of contiguous data to start executing. And you can see all the way through this pattern, it's Y, 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 it's the direction of travel, so the columns. Okay. I'm not going to lie, I have to remind myself of this particular pattern and ordering every single time. We have to think about this in detail. It's a bit like pointers. If you ever come across pointers, you have to go back and remind yourself every time you come and look at it, unless you're doing it day to day. So do take yourselves a minute to get your head around this concept, because it's really important. And try to understand that this is going to be, it is very important for driving good performance in codes. Okay, so what we're looking at is implementing a particular case of this, and I believe the best way to show the answer here is this solution. This is slightly for the next example, but the point is I want to show the kernel off really. This is what I want us to focus on. So here we've effectively got an expansion of our existing kernels before. We are trying to do, we have a matrix A, which we're updating. So matrix A is going to get a constant times 2 vectors. So we need to make sure that we've copied over our matrix A. We're representing this matrix A as a vector here. Okay, it's a contiguous array, C array, type of style array in memory. Alpha was just what we had last time as our constant A. So, and then this time we've got X and Y to give us that extra dimensionality. And we're going to update A with their product of all the elements. Similarly to last time, what we did at the end, we're going to have some limits, m row and n column. This is the same as we had as n length. This is basically the array sizes that we're providing in order to make sure we don't run over the end. And what we'll pass in, we'll show how we set up the execution of this with our block elements and things like that. The really critical thing here to remember is that bit I've just said around the ordering of blocks in terms of rows and column accesses. And what you have is, we've said that the columns run fastest. So X is the thread ID. So X is always going to be contiguous threads. And that is what we need to map to J here. Now, this can be quite confusing, because what you naturally do on the CPU is you say, well, fastest index, that's going to get my fastest running thing. So you need to think about it in the opposite way. What is fastest moving here? J is going to go over a whole column, and then the next column is going to be whatever our row number is times a whole number of columns, and then we're going to do the next column. Okay, so this means that this is the threads run fastest. The thread number that you're associated with the memory is running in the columns direction, and then Y provides us with the index for running the next direction. This allows us to block this up into two-dimensional system and run over the data in the fastest possible way. The best way to get a handle on this is playing around with it in detail and doing it the wrong way around and timing it. So I believe in the example, it's either in this example or the previous one, we have looked at slightly different. We've got something around profiling to look at that. Same as before, when we looked at our block dimensions. So our number of blocks is, we have a block for Y and a block for X. So Y is going first because we're running over the Y dimension. We're going over the columns quickly. And the number of threads per block in each dimension is the same. It's 16. It's 16 times 16. So the total number of threads per block is 256 again. And then we do the same launch as before. The way the example 2.3.0 is set up is there is a profiler in the submit script. There is RockProf that will provide some information around tracing and performance. And when you run it, it'll produce a load of performance files. So obviously I can't produce them right now because we're having teething problems with Archer 2, but I have got some that I've made earlier. And what this is starting to do, if I'm correct, is demonstrate some of the ways to look at this data. Sorry, let me get off that a second. This is called, and what the ROC profiler does is it produces a JSON file that we can load into this tool called Perfecto. This just reads JSON and allows you to look at performance. This can be very valuable. Now, the code itself produces an output and this provides some timing. This allows you to really drill down into it much further and see what the split of timing is coming from what things. So you can see here that creating a stream of execution for the work is taking a lot of time. This is okay. A lot is not. I mean, it's 400 milliseconds. That's a lot in terms of compute time. So all our actual work is over here. I can get this to do the right thing. So I can now see all the elements at the bottom in that region. So stream create took a long time. I've got a bunch of other things, and somewhere down here I should see my kernel. So I've got freeze. That is, it's in timing order. There you go, my kernel. Okay, that's the bit we implemented. The kernel itself is taking 0.2 of a millisecond. And we're only doing it once because we are only calling that kernel one time. And that's not dominating our performance at all. But you could see how if you grew that to a much larger system, that could become dominant. And that's the thing you want to optimize. But because we've looked at that in the recent amount of detail, we managed to get quite good performance. So for those who are interested about making sure they understand the orientation of the assignment of data correctly, I would go and have a look at this and find this my kernel and really get into the process of running a system, profiling it, getting the data out, and looking at it and trying to iterate and convince yourself about the way you need to order the data to the threads to get the best performance. Okay. So, any questions on any of that? This Perfecto tool is just on a web page. It's free to access. There's nothing. It's not something we run or operate. It's quite useful. If I ask for more kernel threads that are physically available, what is going to happen? Well, what you'd end up doing is, I think you'd get an issue, because what you'd basically say is your threads per, are you saying your threads per block gets very large? I think if that's what you're meaning, then what happens is I think you definitely hit a limit, and the compiler will, or the runtime will complain at you, probably the runtime. And probably throw you an error. The other danger is that you lose performance, because what you're trying to do is you want blocks that are big enough to have enough work for a particular group of wavefronts to work together to chomp through all the work. And basically what you're doing by having all these thread indexes and block indexes, you're just saying these bits are independent. Schedule them in whatever order you want. It's not going to affect the calculation. What do you mean by it won't pass? Sorry. Yeah, you'll end if you. Yeah, I don't think it will pass compile. I think it should get stopped because there's hardware requirements that are an issue. There are limits to what threads per block you can have, and I think it's 1,000 and something. But basically, the reason for that is that you actually get into degradation in performance, and tuning that threads per block parameter can provide you better performance depending on how big and what your kernel is trying to do. Because effectively, you want enough work so that the latency of going to get data from memory can be hidden, but you don't want it you don't want to put too much work together that this becomes a synchronization cost of all these threads working together. So depending on what your kernel is, there's a balance there to be had. Okay, fine. Let me just stop sharing my screen for one moment and let me get set up for the next section. So what I'm going to do is I'll go through the lectures for the next part, and then we will see how we're doing at that point at lunch and where we are with the machine. Right. Okay. Everything's still in maintenance at the moment. So I think what I'm going to do is, for the very least, we're going to get to lunch. I'll go through these slides, and then we may take an early lunch and review at 1 o'clock and see where we are. What we may have to do is, unfortunately, we've already rescheduled the final day of the course. It is incredibly rare that we see issues when we run courses. It's doubly rare that we see issues just before we plan maintenance, while we're trying to run a course as well. So I can only apologize for that. It's not ideal at all. Okay, we're now going to talk about managed memory. So the key thing, oh, I haven't shared my screen. That would be very useful. Okay. Right, managed memory. Let's just zoom in a little bit. Okay. What we've talked about so far around memory in our first exercise, and we've used that since in the following couple, is we have explicitly told the runtime when to move data between the host and the device. We have other ways in which to manage memory between the host and device. The different mechanisms can have value in different situations. What we've looked at is this explicit case. So we've had explicitly used pointers to say, create me a host pointer, create me a device pointer, malloc some data on the host pointer, use hip malloc to malloc some data on the device, and then copy data to the destination of the device from the source of some size and give me the direction of travel and the mechanism for doing that. What it's called the kind, copy kind, right? These things. We then use the host, this device pointer to do some execution. We pass that into the kernels. However, the limitation here is that these cannot be dereferenced on the host. So the host cannot look into what's in the data on the device, and we would need to explicitly copy the data back to some form of host buffer in order to look at it. This is fine if we only consider to transfer a large contiguous box of data. It's also going to be the fastest mechanism. However, this can be quite challenging if we've got quite complex data access patterns, if we're trying to do rapid test and development. There's our options which make our lives a little bit simpler here. This is called managed or unified memory. So I think it was, I can't remember who exactly asked this question yesterday around managed or unified memory. The challenge here with this naming, I really, really despise it, is that it is unified to the user. It is not unified in the hardware. And as someone who's interested in performance, I want unified in the hardware, because that means I have got a much faster system, hopefully. In practice, unified in the hardware is not what has been done or implemented. What you're provided is an interface that allows you to access memory in a unified way. Okay, this is called managed memory. You allocate it on the host. this is in place of a sort of a malloc or a new in C++ and hip malloc. You have a single malloc, hip malloc managed, which says, I, hip runtime, now take responsibility for this memory and its locations on the host and the device. I will deal with where it should be. It effectively establishes a single reference to the memory which can be accessed on both the host and device, which means I get past this issue of unable to dereference pointers which are just device pointers. The performance issue here, though, that's introduced is that host to device transfers are managed automatically as they arise. This means if I have some data that's currently being used on the device and I suddenly say, I would quite like that on the host, please, that can introduce a performance hit and will be detected and automatically copied down. So I'm trying to find my diagram from yesterday on a slide quickly to show this. I think I'm going to faff with sharing. But remember when we had our diagram of our picture of the CPU and the CPU memory and the GPU and the GPU memory, the thing that linked the GPU memories was this slower connection that runs around 10 gigabits per second between the two memory spaces. Now that speed's got better, but it is still limiting. What's worse when you use managed memory is that it will, the mechanism in which it works, it gets to the line of code, it then tries to access the memory, it then fails to do it and logs a page fault. The page fault is picked up by the runtime, and the runtime then realizes, oh, I can go access it. I manage that piece of memory. Let me go find the bit you need. It then initiates the copy. What this can mean is that if you're in the middle of a kernel and you're doing something very fast, it's going to call that process in a fast loop. That's going to stop your loop. You stop your kernel executing. It's going to go get memory, and that can be quite slow and stall your processing. Therefore, it's not advised for best performance to go and use managed memory, though it can make it a lot simpler to think about the memory model, and we'll have some of this handled for you by the HIP runtime. Okay, enough of my caveats over my preferences. So a schematic of this might look like we have some double pointer now, which isn't labeled as host or device, it's just a pointer. We've done all this on the host. We then call hip malloc managed on this and give it some size. We can then initialize values on the host. This is fine. We then can just call it in a kernel when we launch a kernel. Okay, we haven't needed to do an explicit copy from host to device. Later, we can come back and grab it back from device to host. Okay, so we can release managed memory with HIP3 as before. This is exactly the same as we had with the hip malloc. Okay, so this is my bit more structured text around my point around the page migration. So the transfers are implemented through a process of page migration. A page is the smallest unit of memory that is often 4,096 bytes on a typical CPU machine. Assume, and this may not be the case in all systems, that the HIP malloc manager establishes a memory in the host space, and we can initialize memory on the host and call the kernel. When the GPU starts executing, any access to the relevant virtual address not present on the GPU, because we've so far just allocated on the CPU, this will issue a GPU page fault. The relevant page of memory that it's trying to access, trying to copy from the hosted device, will then be moved before any useful execution continue. So this would potentially block stuff up. And if you can imagine, if it's doing it for every single page and you've got a very large kernel, if it has to do that lots of times, that could degrade your performance quite significantly. Likewise, if the same data is required by the host after the kernel launch, the access on the host will trigger a page fault on the CPU, and exactly the same process happens. I'm now stalling the CPU, waiting on the data to be transferred, opposed to managing this. Ourselves. So So it's a perfectly fine mechanism to use. It's perfectly valid and exists. It just needs to be treated with care because there are risks, there's performance implications for using it. Okay, so what can we do? So we'll try and help with this. If the programmer knows in advance in this model that the memory is required in the device before the kernel execution, we can use prefetch, basically say prefetch to the destination device can be issued in advance in order to suggest that we're going to move the data in advance of the kernel activity. So it can be viewed as a request to the HIP runtime to move the data. The memory must be managed by HIP itself. Yeah, so we can provide a device ID in which to move the data to. So this is a new command. I don't think we've seen yet. HIP get device, which specifies which of the devices. Now this is important in cases when you start to run across a whole node with 4 or 8 devices in it. Then you need to specify which specific device you're trying to copy this bit of data to. And in the reverse, we can do prefetch back to the host, back to the CPU. And then in this case, we have a HIP CPU device ID to provide instead. Okay, so we can also provide some hints here around and provide advice to the memory manager, the HIP runtime in boards on how you should try and think about managing our memory. What this is doing is basically saying you, the runtime for this particular piece of data, could make some decisions about where's best to keep this data and how to treat it most often. And therefore, you could make optimizations under the hood for us if you were aware of what my intent was as the programmer. So we talked about prefetching, which just goes and gets the data over to the correct location in advance in this memory model. This is more around saying, can I tell you some information about how I will use this data? So we have HIP mem advise. We provide a pointer and a size. We provide a device, and we provide a device in which this is related to. So what are some of the different types of advice we can supply? HIP mem advise sets read mostly. Data will mostly be read and only occasionally written to. That means that it's unlikely we're going to be updating this and we're going to need to sync across the host of the device. HIP mem advise set preferred location sets the preferred location for data to be to the specified device. So that can be the CPU, a particular one of the GPUs on the node. We can specify which of those are preferred location for this data, and it will try to keep it there unless we use it and access it from another device. HIP mem advise set access by. Data will be accessed by the specified device to prevent page faults as much as possible. So you can say it's going to be accessed by this location. That's the place you should try and keep it. Or you can set coarse grain. So the default model is fine grain that allows coherent operations between host and device while executing kernels. The coarse grain setting can be used for data that only needs to be coherent at dispatch boundaries for better performance. This one's a little bit more complicated. We're not going to look at these in great detail, but you should be aware that the concept of device, advice for managed memory is available, and that it could offer you potential performance benefits. But once again, the way to look at this is, if you're implementing in this memory model, is to go and test it and do profiling of your code in order to verify which settings are best for your particular kernels or the different sections of your code. Again, the relevant memory must be managed by HIP. This must be a HIP managed memory setup in order to take advantage of this. If you are going to explicitly copy data to and from the device, then you won't be able to take advantage of this, but then you should be explicitly keeping data in one location or the other. Okay, so when to use this, often the start development testing and with managed memory, and then move to explicit malloc and memory copies as required for performance. So use managed memory to kind of get the system set up and running, and then do explicit copying in order to get performance out. Okay. Ignore this time. We're going to take we're going to have a rest of the time until lunch to look at this. So in the current direction, we have supplied the exercise from the previous section. This computes the operation aij equals aij plus alpha times xi plus yj. This is the thing up here. It may be used to run unaltered code once as a reference with RogProf, so we're going to get some experience using RogProf. Output to show the times in different parts of the code. So RogProf can be used to show this. You can get a CSV out and look at some of the data on the terminal, or alternatively, you can download the JSON it produces and upload it to Profetto via the web. Okay, if you just Google Profetto, you'll be able to find that profiling tool. So what you can do then is start to replace the explicit memory management in the code with managed memory. So do this for both DA and HA, and by a single declaration of A. So what you can do is remove DA and HA and have a single A instead. Run the new code and check what the answer is correct, check what the performance is like, and then add relevant prefetches and other parts of this to this code device to try and get better performance. Okay, there's a little bit of an extension task for people. So what we're going to do is try programming that up until lunch. What we'll do is, I think it's best if people do have a look at this. You can compile the code on the login node and see if you can get it to compile correctly. And I will see how we're doing on Archer 2 fixes, and then we can try hopefully run some tests of that. Are there any questions before we move on to this exercise? Hi, well, sorry. For device ID used in HIP mem prefetch async, is this always just the idea of the GPU in both directions? I both transfer to and from GPU? No, it's not specifically. So you're always prefetching to a particular device. So the CPU has a device ID. That is, let me just get the section of the slides back up. So if you see in section 2.4 of the document, you also have this line. So prefetches from the device to the host can be requested using a special destination value, HIP CPU device ID. Well, then that obviously asks the question, how do I get said HIP CPU device ID? The thing here to remember is that you could have multiple devices in a node and they would each have different device IDs. And you would need to, so you can also have memory copies between devices. So we're mainly focusing on just having a simplistic case here where we have a host and a device and nothing else involved. So I'm just trying to find the API call that you'd need. Get. I'm making a mistake here. That is HIP get device, and you already have a device ID. Yes, but how is CPU device set? Because oh, no, I was right. Hip get device provides a device ID into the integer device ID. Just can't see that example one where this hip CPU device ID is set. Yeah, you'd think it's just an API constant. Oh, sorry, it says that. It is a special constant. Right. Fine. Sorry, that just seems kind of odd to me because you could have a GPU node with 2 sockets, but I suppose AMD haven't tended to go down that path. They've tended to have a single CPU with multiple NUMA regions, but one CPU nonetheless in their GPU designs. So that probably makes sense for them. Okay. Anyway, well, that's how that should work. Okay. It's now 12 o'clock. We're going to stop for lunch and we will start again at 1. We will briefly look at this example and then I think Juan's going to take you through shared memory and constant memory this afternoon. Okay, thank you all for this morning and apologies for the disruption. We can't always be perfect with the machines being up all of the time, and it's just a little bit unfortunate we had to delay the start today. We'll try to answer them as when they come up, but we'll see you at 1 o'clock.